Welcome engineering statics students. This is another quick video mini lecture in reviewing properties of vectors that are often used in engineering statics. This is appropriate for Washington Community College ENGR ampersand 214 statics class. And the topic of this mini lecture is the vector dot product. So in previous lectures we talked about what are vectors, vectors versus scalars, how to represent vectors in terms of magnitude and an angular direction versus some kind of reference angle, or in terms of the I hat, j hat, k hat unit vectors that correspond to the Cartesian xyz coordinate axes. We also learned about how you add or subtract vectors by adding or subtracting their x, y, and z subcomponents and doing tip-to-tail kind of graphical representation, addition, subtraction of vectors when and only when the physical length of those vector arrows represent the vector magnitudes. So mathematically, addition and subtraction is great, but we like to multiply as well. So the other types of operations that we can do with vectors, just like we can do with scalars, is multiplication. And the big difference between vectors and scalars is vectors have two different distinct multiplication operations called the dot product and the cross product. And we're going to talk about the dot product for this lecture. It's also known as the scalar product because its result is actually a scalar, not a vector. So you multiply two vectors together and you get a scalar. For the purpose of engineering statics, the most important aspect of the vector dot product is it returns, by definition, the magnitude of the portion of those vectors that are parallel to each other. And there's all kinds of times that we really have to know what's parallel, or we need to define something important in terms of a parallel portion. So that's really the way we use the dot product in statics. So we're going to start with definitions. So if I got two vectors, A and B, and I multiply them together with the dot product, otherwise known as dotting them together, and to designate that, you're going to use a physical dot. Don't use a little star like you would for scalar multiplication, like the asterisk on your keyboard, and don't use a cross because that's the cross product and it's a very different operation. Just use a little dot, literally. That is equal to the magnitude of vector A times the magnitude of vector B times the cosine of the acute angle between them. So now we got to get graphical. So we've got vector A and we've got vector B heading along on some line of action. We often represent force vectors on their lines of actions. So we'll just slide vector B to where along its line of action to where it's easy to see versus vector A. So here's our cosine between that we care about. So what do we know about cosines? It's adjacent over hypotenuse. So this says if we make a right angle, say here, there's our right angle sign. Vector B is now the hypotenuse, and the cosine of theta is now this, which, doggone it, is parallel to vector A. And if I were to do the same thing with, I'll draw it a little further out, if I were to do the same thing, make a right angle, say here, oh well, I'll extend my line of action because I'm now using the length of vectors to represent their magnitude. So if I were to do the same thing with vector A, make a right angle such that vector A is the hypotenuse. And actually, let me start over again with that. In order to do that, I would have to move vector A along its line of action a little farther. if I'm going to use its magnitude. I would have to move it up here, index it along. I would translate it down its line of action. Drop a perpendicular such that vector A is the hypotenuse, and now the cosine of that angle multiplied by the full length of vector A would give me this portion. Oops. This is 90 degrees. This is the hypotenuse. Looking at it upside down. Hypotenuse. Tenuse. Adjacent. Oh, upside down trig. Okay, so you can see that by taking the cosine of theta times the full length of A, once we've indexed it up along its line of action, so we're taking its full length represented by the vector arrow length, dropped, made that the hypotenuse, so the adjacent, which is obviously parallel to vector B, would be what we would get, or its length would be given by cosine of theta. So basically use a right angle ruler if you need to. So remember which one is the hypotenuse. So that was a somewhat messy graphical representation of getting which portion of either one of these vectors is parallel to the other. The nice thing is at the end of the day it doesn't matter, because you'll get the portion of each one that is parallel to the other regardless. So let's do an example of this. I'm going to draw a couple of lines of action of vectors in 3D, where I'm not even going to be tempted to try to graphically represent those right angles that are kind of hard to draw. So I've got a vector A heading along some line of action. And I can represent vector A as, let's call it I hat plus 4j hat minus 6k hat. So I'm going to use my coordinate unit vector designations to show that it's heading, it's heading a little in the positive, it's heading over in the j hat direction, it's heading down. And I have got another vector out in space, 3D, vector B, and I can represent it as, so it's heading probably in the negative I hat direction. It's also heading in the positive j hat direction. It's going up. So I think it's not going up quite as much, but it's going up. If I wanted to know which portion of B, what is the magnitude of B that is parallel to A, I could use my dot product to get that if I knew the magnitude of A and B. Which brings to mind, how do I find vector magnitude? So that may or may not have been something that you've covered in another video, but in case it hasn't, we're just going to review it really, really quickly here. Just to review, the magnitude of a vector, we can use expanded Pythagorean theorem, would be squaring the magnitudes of all three of the component directions, and if one of them happens to be 0, that's no problem, and take the square root. So it's like a big long hypotenuse. So we can do that in each one of these cases, we can get the magnitude of vector A. It's going to be the square root of 1 plus 16 plus 36. And vector B, magnitude, vector B is square root of 4 plus 9. We can crank through the arithmetic later. Make sure we don't make a math error. Okay. So we now have each one of these already. And if we wanted the cosine of the angle between them, we would need to know some other way of actually algebraically calculating this dot product. So we've got a good idea of what it means in terms of lengths and cosines of angles between, and that angle is going to be some crazy, 3D angle out in here somewhere. That's theta. Now we need to define a way of algebraically cranking out our dot product. So as it so happens, and this is just definition of vector algebra, A dot B is AX BX plus AY BY plus AZ BZ. And we can actually prove why that is the case by doing the FOIL method. We can multiply our vectors out. And I won't go through the whole thing because it's kind of long. But this also we got a circle where we wanted a parentheses. So we're going to dot this into B. Bx I hat plus, so these are each component, these two vectors. We can FOIL this. So if I multiply A sub x, which is the scalar length of the portion of A that's going in the I hat direction, times dotted into B sub x I hat, I'm going to end up multiplying the two scalar components together as scalars. And then I'm going to end up with their vector components dotted into one another. And I can continue, foiling. Oh. Getting a little busy here. This is the important example. So I would just keep doing my FOIL multiplication, which is, following general rules of scalar and vector multiplication, and would end up with I hat dot j hat plus, and I would go all the way through. I would end up having 9 different components that I would add up. So here's where we can revert back to our geometric definition of the dot product and say, okay, we're always going to be multiplying the two lengths, which for instance we do here. Here's the length of A sub x times the length of B sub x. And now I'm going to multiply the length of unit vector I times the length of unit vector I. Well, each one is length 1. I have 1 times 1, and then I'm going to multiply by the cosine of the angle in between. Well, they're parallel, so the angle in between is 1. Likewise, when I come over here and I'm looking at I hat dot j hat, those are the x and y coordinate axes. They are at right angles. They are perpendicular. So the cosine of two things that are perpendicular or at 90 degrees is 0. So any term that is not going in the same direction is 0 by definition, which is why we end up with nothing more than the like directions multiplied and all added together. And this is, of course, a scalar. So that's why it's called a scalar product. So once we have this value, it goes in here. We've already determined this with our Pythagorean rule, and we've determined this with our Pythagorean rule, and we could divide this term by those two, and we would be left with the cosine of the angle between the vectors. So that's one way that we can use the vector dot product to find the actual angle between things. We can use this relationship of being able to algebraically express the dot product using our rules of vector multiplication once we have the vectors expressed in terms of I hat, j hat, k hat. And if we know any of the other terms, we can get the one that we don't know. So if, say, we knew the length of vector b, we knew the angle between, and someone said, well, you know, what's the length of the portion of A that would be parallel, we can just solve for that. So that gives us a way to find any one of those terms. The dot product is also used definitionally to define something called directional cosines. And for a single vector, direction cosine is simply the cosine of that vector with the coordinate axes, which is, interestingly enough, ends up being nothing more than the length of that vector that is in that direction. So sometimes a vector is described in terms of its directional cosines, and that is basically an application of the dot product with respect to the coordinate axes. I won't talk about too much about that. It's not used extensively, but it's a term that you might run into. So I wanted to at least just cover it in terms of it would basically be, let me just draw it here. If we had a vector and it's vector A and it is making different angles with the actual coordinate axes, we can define the direction cosines as the cosines of those angles that the vector makes with each of the coordinate axes. And so we can relate those to vector A by remembering that that would be defined as, in this case, A dot I divided by the magnitude of A times the magnitude of I hat, which is of course 1. So we can use the definition of the dot product to define what's known as direction cosines, or the cosines of the angles that that vector makes with the coordinate axes. It's another way of denoting direction, but it is effectively based on the dot product of dotting a vector into each of the coordinate axes. Just another way of telling direction. But if you run across someone wanting to know direction cosines, just remember to use the dot product and dot that vector into each of the coordinate axes, and then make sure you express it as just a cosine, which by definition will be a number less than 1. So you'll have to use the unit vector, the unit direction of that vector. Great. So that is the end of this dot product lecture. So stay tuned for more information on cross products, which will be a prelude to discussions of moment in engineering statics.